There's something more that we need to discuss besides just how much force you apply. Because with a needle, with very little force applied, it goes easily into an object. The reason for that is the intense pressure that it would have. Simply because you apply very small force over an even smaller area, very, very small area, obviously, with a needle, and so that results in a very, very high pressure. Now, the same idea, just kind of in an opposite way, is true with the traditional bed of nails trick, where a person lays down on a bed of nails, and generally they'll have some sort of concrete block on their chest, and someone will come along and break it with a sledgehammer, all sorts of crazy stuff, but yet they don't get punctured by any of the nails. The reason why is all of these nails individually create a very, whenever you add them all up individually, they create a very large surface area. If there was only one, quite obviously, the person, you wouldn't have to push on them at all. It would puncture the person and hurt them severely. But with a whole bunch of nails, you have a very, very large area. Because that's such a large area, their force being applied down on it, divided by a very large area, creates a very low pressure, and they actually lay on the bed of nails unharmed. Now, pressure is actually caused by individual gas particles which are constantly moving around, bumping into the walls of the container and into each other, but they're moving at some velocity, they hit the wall of the container, and they bounce off. And this would be an elastic collision that's occurring here, and so because of that elastic collision, the wall gets pushed outwards. That's going to end up causing our pressure of a gas. Another thing that is of note is that pressure is equal at any given spot in a gas or a fluid. So here we have water, and the pressure that you will find here at the very top is all exactly the same, no matter the shape. Same thing down another depth. It doesn't matter the shape. Notice that the water height rises to the exact same place. It doesn't matter the shape. The pressure is going to be the same at all the same heights. So the pressure at A, B, C, D, and E are all equal, even though the differing shapes and the differing quantities of water makes you think, well, for example, C seems to have the most water over it. It should have a higher pressure. No, it is at the exact same depth. Notice how all the water heights rise to the same place. Now, this idea is very important with many applications, hydraulic applications. For example, hydraulic lift here, because the idea is the amount of pressure you put in on a very small area, pressure in, is going to equal the amount of pressure that's used to lift the car, pressure out. Which then you might think to yourself, well, I'm not able to apply all that much pressure. That's why we use a smaller surface area, because remember, pressure is force divided by area. So if you apply your force over a very, very small area, and then that gives us some pressure, but then that pressure is applied over a very, very large area on the other side, we will get a much, much larger force lifting it up. Now, this doesn't actually contradict work energy theorem, or excuse me, conservation of energy, because the amount of distance that it goes up would actually be much less. Energy is still conserved, which means in this scenario, the work that you put in is also going to be the work that is done out. And you'll see from another calculation, what's going to happen is while the force gets multiplied because of constant pressure, the pressure you put in is the pressure used to lift the car, the distance will not be the same. You'll have to travel a much further distance to cause the car to go up a very small distance because of the multiplication of force. This actually operates almost exactly the same as a simple machine. Remember, in a simple machine, you're actually trading force for distance. An increased force, a multiplied force, but a reduction in distance. All right, a couple of example problems now. Something that all of us have experienced whenever we go down to the bottom of the pool, depth of maybe around 2 meters, where there's a pressure of 121,500 pascals, a little over 100,000 pascals. How much force does the human ear experience? We all felt that there seems to be a lot of force. So exactly how much is that? Well, the other thing you need to know is the area of the human ear drum. That's about 1.5 times 10 to the negative 4th meters. Now, I would like to point out, because in most problems you're going to end up having to do this, and in the next problem we're going to end up having to do this. Where did this area of 1.5 times 10 to the negative 4th came from? Well, it came from the idea that the human eardrum is approximately circular, and I was able to look up the radius, about 0.7 centimeters, area of a circle, pi r squared, and so that allows me to calculate the area. Also of note here is I converted from centimeters back to my base unit of meters before calculating the area, not afterwards, because this needs to be area in terms of meters squared. So if I went ahead and did this in centimeters, I'd have an area in centimeters squared here, and the conversion factor from centimeters squared to meters squared is different from what you're used to. In other words, just make sure to convert first thing before you do anything else. Of course, here the next algebraic step is to multiply what's in the denominator over. So whenever I multiply 1.5 times 10 to the negative fourth over to the other side, I end up with a force of 18 newtons. 2 sig figs, I had to come back up and give myself an extra significant figure there. Now, this doesn't feel like a lot of force, but the human ear, especially the eardrum, is a very, very sensitive spot. 18 newtons of force applied directly to the human eardrum can actually cause a decent amount of discomfort. Now, the way a car's tires work is, of course, you generally have 4 of them, and whenever you apply weight to them, like the weight of a car, they're going to end up squishing down just a little bit to where they're not just touching at one specific spot, but, maybe 4 centimeters of the tires touching, and so you have, if you will, approximately a rectangle of the car touching the pavement. The width of the tire, right, that would be how far it is inwards on it, and then in that picture, and then the amount it squishes down onto the ground, that would be this length right here. And then I tried to redraw that rectangle here to where we can see that there is a part of the tire touching the pavement. You have a width and a length of that, and that's going to give us our area down here. The next thing that we have to think about is what is actually our force getting applied to the tires? What force is pushing down on them? Well, it's the force of gravity of the car, because the car is mashing down into the tires, which is actually equal to the normal force pushing back up. But we can just simply understand it for now as the force of gravity pushing down into the tires. And I also know an equation for the force of gravity. Force of gravity is mass times 9.81. So I substitute everything in. Mass of the car, 1,200 kilograms, 9.81 for gravity. These two are the force. Then I have my area of the tire, 0.04 for my 4 centimeters, 0.125 for my 21.5 centimeters, the width of a tire, if you will, and a 4 out in front, 4 times those things, because there are 4 tires, so I need 4 times the area. And I end up with just around 340,000 pascals with my 2 sig figs given here, minimum spot for sig figs. That's around just a little under 50 psi, which is about what you would want to, it's in the range, maybe a little high, but about what you'd want to inflate a tire to. Lastly, I want to work a hydraulic jack problem. Now, the idea with a hydraulic jack is that you apply force to a very small area, and because you're applying your force to a small area, you end up getting a large pressure, even though you can only apply, relatively speaking, a small force. But in an enclosed fluid, the pressure inside is equal throughout, meaning that whatever pressure you apply into the fluid, whatever you push in with, is what pressure must come out to lift something, let's say a car here, and as long as that area is much, much larger, you're going to get a multiplied force. Exactly the same as you would with simple machines and mechanical advantage. The advantage with hydraulic-based systems is it's a lot easier to change the area, because that's what we're doing. We're just changing the area to increase the force than it is to go out and find an incredibly long lever, like you might whenever you're doing middle school mechanical advantage. Now, like I said, the way you would solve these problems, you're going to apply a pressure down, and that pressure is going to lift the car up, and the pressure is the same. Whatever you apply in is what comes out. And we know the equation for pressure, that's force divided by area, and so I'm labeling force in, area in, right, for my pressure in, and then of course my outs for force in area for my pressure out. Let's pause for a second and actually do a variable bank just to make sure we got everything straightened out here in this problem. I'm looking for how much force the mechanic must actually exert to lift the car on the jack. In other words, how much force must he put into the system? So F in is what I'm looking for here. We'll talk about F out here in a moment. Now, I also gave you the areas. The area in, aka the area of the small one, is 0.040 meters squared, and a lot of times you wouldn't be given the area. Like in the previous problem, you might have to calculate that. Maybe this is a circular area here, and they give you the radius or the diameter, pi r squared for the area. And I also gave you the area out, the area that's used to lift the car. The out is what's being used to lift the car. It's the pressure that's coming out of the system, and you're the one putting the pressure in. Now, talking about the force out, how much force do we need to use to lift the car? Well, remember, back multiple units, and we've been using it throughout the statement that the minimal amount of force needed to lift an object vertically is equal to the force of gravity. So how much force do I need to use to lift? Well, it's going to be the force of gravity. And thankfully, I do know the mass of the car, which would allow me to calculate that. All right, so substituting in everything that I know, I'm looking for Fn. Here, it's the force of gravity, and the next step I'll break that to mass times gravity. I do know the mass of the car, and so then I'll substitute in numbers, and we'll be able to solve for how much force the mechanic actually has to put in to lift this 11,000 kilogram car. So after working this simple algebra, just taking all this, shoving that into the calculator, and then the next step came out with 7,194. Next step, multiplying what's in the denominator over to the other side, I come out with 290 newtons is how hard the mechanic will actually need to press down. If we were to compare this to a simple machine and actually look at the mechanical advantage it offers, mechanical advantage output force over input force here, and so whenever I put my output force, how much is needed to lift the car, 10,000, almost 11,000 newtons, and how much the mechanic actually had to put in, 288. This gives us a mechanical advantage of well over 37, almost 37.5, 38. That's a massive mechanical advantage that you wouldn't be able to achieve with just a simple machine. Now also, just like with simple machines here, there's a trade-off that occurs. You trade off, you go a further distance, you push downwards further, but because you get to go a further distance, you get to use less force. Now the same thing is said here. We are going to, or the mechanic here, pushes down with a much less force, 290 newtons, but because of that, it's not going to go as far. The reason that the car isn't going to lift up as far as he pushes down, he's going to push down on this thing 32 centimeters, is because we learned in our last unit, energy is conserved at all times. No energy is created or lost in this system. Just because he's using less force doesn't mean that energy was created inside of the system. Because we can say that no energy was created or lost, energy was conserved, we can say that the work that the mechanic does in, how much work he puts in, is the amount of work that comes out, lifting it up, because work and energy, the same thing. So these two works must be equal to each other, and I know the equation for work. So work equals force times distance, and I'm still labeling with subunits what each thing is. So substituting in my knowns, the force out is the force of gravity of the car, mass times gravity, 10,791. That's this portion here, right? The force out, the minimal amount of force needed to lift the object is equal to the force of gravity. And now it's just algebra to be able to solve for the distance out, or how high up this car is going to go. And so after going through the simple algebra steps, dividing both sides by the 10,791, I come out with 0.0086 meters is how high up it goes, or about 0.86 centimeters, jumping the decimal twice there. Look at the comparison. He went down 32 centimeters, pressing down, and it didn't even go up. The car didn't even go up a single centimeter there. The reason for that mechanical advantage, work is the same, and so we're making a trade-off here. Much less force, a reduction in force, but because he makes his job easier, so to speak, by reducing the force, he doesn't get the car to go up as far.